What's that? Oh, well, I put yours. Okay, well, I just grabbed one. I forgot. I didn't even look. This is yours. All right, so we're talking about local linearization. I want to kind of show you what this would look like. So the point of everything we're doing right now is we're trying to find the slope of the tangent line. So, or the equation of tangent line. So like there would be the tangent line right there. There would be the tangent line. Tangent line right there. Tangent line right there. Tangent line. So, pretty much anywhere that you are along this function, you can have a tangent line. And if you want to, you could write the equation, and that's what you've got to do. There is a homework assignment that's due tomorrow. Okay, if you haven't started on that, there's only one due this week. All right, and what we were working on yesterday was we were looking at some graphs, and we were sort of zooming in on those and drawing little straight lines that would represent the tangent line in a really, really, zoomed in location. So for instance, like right here, tangent line might look like that. Right here, tangent line might look like that. Right there, there. So on and so forth, right? So what I want us to do today is we'll kind of compare, and then we're going to start putting some numbers here. Now they're going to be approximations for the slope of those tangent lines, okay? But we're going to start noticing a trend, because then we're going to graph them, and then we're going to start noticing some trends here, okay? So, for instance, now we can talk about some easy ones here. These two completely horizontal tangent lines, they have a slope of 0. How do you describe these tangent lines? What are their slopes, rather? Positive. Are the slopes, the positive slopes, are they getting larger or smaller? Probably larger. So this might be a 2, this might be a 4, this might be a 6. So go and throw some numbers on there, and we'll on your paper if you don't already have them, next to your little local linearization segments. What about right here? What do we think is going on right there? Positive, negative? Probably negative. I might put like maybe like a -1. And how would we describe these over here? Kirsten? Positive slopes, negative slopes, 0 slopes? Well, you might think they're negative, but they're not. If you're standing there, they are positive, because we're reading kind of from the left to the right. They look very similar to these, in fact, right? However, notice this one is a little bit more flat than this one, and this one is kind of in the middle. So this one's kind of steep, but not too steep. So I might call that one like the 2. I might call this one the 4, and I might call this one the 6. Now, of course, I zoomed in way too far. This is what I should have done. So I'll have to get caught up to y'all here in a second. So we had 2, 4, 6, -1, 0, 2, 4, 6. And so what I want you to do is underneath this graph, draw another xy axis. And what we're going to do is at the same x values as this graph up here, we're going to plot those slope values. Okay? So for instance, at x equals 0, I'm going to plot the point -1. Over here at x equals 2, the slope was 0. So I'm going to plot the up and down point 0, the y value 0. Here at 4, at x value 4, I had a y value of 2, so I'm going to put a, I'm really just eyeballing this here, okay? So this is, we're sketching. That's okay. Then over here at x equals 6, we had a y value of 4. And kicking over here, we had a little y value of 6. But we can definitely see a trend, and that's kind of what we thought. So these y values, these up and down values, are graphing the slopes here. I'm going to move a little bit to the left. Here around -1, -2, I'm going to have a slope of 0. Kicking a little bit farther this way, around the -4 on the x-axis, or I'm going to have a slope of 2. And then kicking over a little farther left, I'd have a slope of 4 and a slope of 6. And we kind of look at that and we say, wow, there's a trend there, Mr. Goddard. I say, yeah, there is. So looking up at that first function, at this first graph, what is its function family? Anybody remember what graphs look like this are called? Sarah? Just you got to guess sometimes. That's fine, I forgot a name. Robert? It's a cubic. Now what does a cubic look like? It's normally like f of x equals, yeah, something x to the cube. You know, it might be like, there might be an a, and it might be like a plus b x, blah, 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 you know, plus blah, blah, blah. But there's going to be something x cubed. What does this look like? No, it looks like a smiley face. That's why I'm smiling. Right? Yes, that is a quadratic. And that would be f of x equals something x squared. Like, you know, I'll put b x squared plus blah, 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 blah. Other stuff like that. What's interesting is that this, and we'll go ahead and label it, this is a graph of the tangent lines. Actually, it's a graph of the slope of the tangent lines, m tangent. Slope of tangent lines. And what was interesting is that that graph itself is also a function. So we had some function, and then we found all those slopes, and we plotted those points, and it was also a function. All right? And in fact, that function, this one down here, has a special name. It's called the derivative. So if you want to pull out your notes real quick. This is still 3.2, you could say. The graph of the slopes of the tangent lines is a function. And it is called the derivative. technically, I'll give you the whole thing. It is called the derivative of f of x. Say that again. Mm-hmm. So the graph of the tangent lines is a function, and it is called the derivative of f of x. It also has a special notation. All right, are you ready for it? F, and then this little hyphen thing here, which we call prime, and then x. So we call this f prime of x. So we should call this that's f prime. In fact, if you look at the name of your homework, what's the name of your homework there say? Graph of f and f prime, right. I think in the notes I did have some, there are some other names, and I'm just going to, might as well tell you right now. Sometimes it's also called, or it's also written as this, dy over d of x. And another form is d over dx of f of x. It's also sometimes called y prime. Part of it is because whenever they were discovering calculus, there's a couple of different guys. I think it was definitely Newton, but I think the other guy was Leibniz. And they kind of discovered it kind of at the same time. And they had different notations because they were kind of just working on their own doing these discoveries. So, all right. So we're going to kind of do our own sort of discovery and notice some patterns about the relationship between the function and the function f prime, that is the derivative, and the derivative telling us the slope of the tangent lines. The really neat thing is, if I am able to get this very quickly, then remember how we found the slope of the tangent line the other day? We had to do the limit of the difference quotient, and we had to do all that crazy algebra stuff like that. If I have this, then I can just be like, what's the slope at 4? Oh, looks like it's 8. And I can just kind of look at this graph, and I can do some things like that. All right, let's go ahead and go over to this one. I think we already might have some number. We don't have numbers there. What about right here at the vertex? What would you think the slope would be? 0? What about right here? Sure, we'll call it 2. What about right here? 4? Over here? -2. I'll try to make it kind of symmetric. -4. So beneath that, come on now. We will sketch an xy axis. And at the same x coordinate, so at the same left and right spot, I'm going to make my up or down value, my y value, equal to the slope here. So at x equals 0, I'm going to have a y value of 0. So actually, that puts me right there at the origin. Working my way to the right, around x equals 2, I'm going to have a y value of 2. Not because this does happen to also have a y value of 2, but because we've determined that the slope there is 2. It's about a steepness of 2. Kicking over a little bit more, we've got around 3 and 4. It looks like we've got a steepness we've determined to be about 4. So I'm going to kind of put it up there like that. Kicking over here to the left of 0, looks like I've got a slope of -2. So remember, that -2 is going to be my y value. So I'm actually going to kind of go down. And then kicking a little bit farther over to the left, my y value is going to be the slope of this. So we said the slope was -4. So I'm going to go down 4. Whoa, what do you know? All right. So let's talk, class. What sort of graph is this? It's a quadratic. So f of x was quadratic. What's f prime of x? It's a line. We normally would say linear. Linear, actually. If you have a function that's a cubic, it turns to the derivative is quadratic. If you have a function that is quadratic, its derivative is a linear. I wonder if that's true all the time. Tell you what, while I take attendance, finally, y'all take care of number 1. Because what's the difference between number 1 and number 3? Yeah, it's upside down. It's a frown, but still a parabola. Mm-hmm. Oh, okay. You got some numbers there. 0. Not quite on those. Let me see if we can verbally walk through some of those here. Your linear lines, your linear approximations, look good, but your numbers are just off just a touch. So I saw you had So walking around, I saw a lot of you have 0 right there. Kirsten, what kind of numbers are these numbers? Positive or negative? They are negative because remember, when we look at slope, we read it from left to right. You know, if you need it at the top of your paper, right, make it like this. Do the slope chant. Positive, negative, 0. No, that stands for no slope. If you need to do that, do that. These are definitely negative. Now, if we're going to, now remember, if you need to write something else on your paper, you'd say slope is steepness, okay? So, going from here to here to here, is it getting steeper or is it getting shallower? From left to right, looking at this one, this one, this one. Well, if I was on a sled or in a car or a bike, this would be okay right here. This would be like, all right, I'm starting to get some sweaty palms, getting a little worried. Here, I'm, praying for help here because I'm about to die, about to go into free fall, right? So we already said that those are negative. So this would be like a -2, -4, -6. These over here, climbing the mountain, really hard to climb here. So that might be like a +6. Kind of hard here. That would be a 4. This one, not so bad. I can handle that one. So around here, this is my 0 point. We've kind of been going from that 0 and then working our way left and right. So here we're looking at like a -2 on our y value, a -4, a -6. Kicking over to the left here, we see like that's like a +2, +4, +6. We should have something kind of like that. All right, now this isn't being asked, but this is part of the reason why I'm giving this assignment, is for us to do a little bit of reflection. Yet again, what type of a function are we seeing right here? It's a quadratic. It's something x squared plus blah, 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 blah. I'm not really sure. But over here, for the derivative, so if I say this is f of x, f prime of x, what type of function is it? It's linear, which has just something like mx plus b. All right? Come on in. So I think we could all sort of say, yeah, I get it. If it's cubed, the function is cubed, is a cubic, it's going to turn into quadratic. If the function is quadratic, then the derivative is going to be linear, right? I wonder what a linear function would turn into, right? Yeah, that's a good question. But I don't have a linear right there, so let's just go ahead and draw a linear function over here and do our own. So on our notes, Mitzi, I'm going to leave that there for you. That's a really good thing to write down in your notes. I've also got the video rolling. So there's our function y equals mx plus b. Let's go ahead and do some local linearization on it, shall we? Right here, the slope looks like a line right there. Right here, looks like a line right there. Right here, looks like a line. Right there, looks like a line. Right there. Yep. Okay. Is the slope changing on those tangent lines? Nope. Robert, give me a number for, I guess any one of them, because they're all going to be the same. Okay. 1, 1, 1. It's definitely positive. Slope of 1. So when we graph that, all right, I'll start here around x equals 0. The up-down value is going to be 1. When I go over here, the up-down value is going to be 1. When I go here, the up-down value is going to be 1. 1. Right here, over here, the up-down value is 1 because my y value is whatever the slope of the tangent line is here. So this our original function is something like mx plus b. It's linear. The derivative, anybody know what type of a function this is called? Not a zero function. What's that? It's a always the same function, but we don't say always the same. It's a constant function. So f prime of x is constant. The way that its function family it looks like is f of x equals b. Like in this case, f prime of x equals 1, or it could be like -1 or +10 or something like that. It just depends on what the slopes are here. So that's great for polynomials. We see that cubics go to quadratics, quadratics go to linear, linear go to constants. Now I wonder what would happen if we were to take the derivative of a constant function. Let's just do it for this one right here, shall we? What is the slope right here? Sorry, I'll start drawing some local linearization. Kirsten, slope. What's the slope right here? It's 0. What about here? Here? Yeah, it's always 0. So it's the same kind of thing as you get from up here, only now it's always 0. So if I were to plot those, my up-down value would be 0, 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 0, 0. This is also a constant function, but it's a very specific constant function. It's the 0 function. I don't know if it's called 0 function, but it's the function who always equals 0. So this is just 0. F prime of x would equal 0. Actually, technically, what this would be, this is kind of fun. Robert, you might like this kind of thing. What we just did here is the derivative of the derivative. Do you see that? Because we had the original function up here, and then we found the slopes of those tangent lines, and we plotted them here. So that's called the derivative. And then we actually did the same thing again with this one. And so we took the derivative of this derivative. And that actually is a thing. We will talk about it next week. It's called the second derivative. And it's called f double prime. I just kind of got super excited and couldn't stop teaching you all on this. So if we have the first derivative and the second derivative, you might ask. Go ahead, you can ask. Absolutely there is. Yeah. You just take the derivative of this. Now it's going to get pretty boring really quickly because what's the slope here? What's the slope here? So what's the graph of the third derivative going to look like? Exactly like that. Yeah, the derivative of a constant function is just 0. All right? So any constant function, even if it happens to all be zeros, then the derivative is still zeros. Okay? Now, we're starting to recognize the trend, but we don't have a straight-up formula yet. Okay? We can't just, we'll get that formula tomorrow. Okay? But I think it's enough right now for us to kind of get in our head, and Mitzi, this is what you missed. When you've got a function here and you find the slope of the tangent lines and you put numbers on those, then you can graph them, and that graph is called f prime. That graph is called the derivative. And cubic graphs generate quadratic derivatives. Quadratic derivatives create linear derivatives. Linear derivatives create constant derivatives, and constant derivatives create 0 derivatives. Do we need to write that down? I think I've said it like a million times. I'm going to try to do it in symbols, but we'll do something more interesting on that later. So the rest of this homework, though, was not so nice polynomials. There are a bunch of rational stuff like that. So let's go ahead and analyze a problem like this. because I'm talking about this Thursday. This actual online homework will be due a week from tomorrow on Friday, but you're going to have to do it, so you might as well talk through it. So let's go ahead and look at our local linearization. There is an asymptote here. For whatever reason, my graphing software doesn't show it, but there's an asymptote there. That's fine. Let's throw some numbers up here. On this section of the graph where we're going through the waterfall, are these slopes positive or negative? Going to you, Syra. Positive or negative for the numbers here? Well, negative. Probably something really close to 0 here, okay? But it's not 0. I mean, I guess maybe we could put 0. But it really isn't. It's not totally flat. It's still getting closer and closer. There's actually an asymptote here at 2. I might put it like negative 0.1. And then this might be like a negative 1. Getting a little bit steeper, a negative 2. A little bit steeper, maybe a negative 4. A little bit steeper, maybe like a negative 8. Going down the waterfall. Robert, what kind of slopes are you seeing here? Positive or negative? They're also still negative. Yeah, coming down the roller coaster. This super steep negative, something like maybe negative 6, maybe like a negative 2. And this is flattening out, but it's still negative. See, it's still going downward. So maybe like a negative 1. So this is f of x. This is rational. We don't have as many nice, I mean, it's just rational. That's just the things that have the asymptotes and the little sort of hyperbolic type things going on there. Those are rational functions. So we're not going to get as nice of a relationship like you saw between the cubic and the quadratic to linear and so on and so forth. So Mitzi, what we've been doing here now is on this graph, which we are sketching immediately below and labeling it f prime of x, at each of these x values, I'm going up here and looking directly above it, and I'm saying, all right, what was the slope? And based on that slope, I'm going to make that slope my up or down y value. So like negative 0.1 would be kind of like right here, because it's negative, so I'm below the x-axis, but not very far. Then right around here on the negative 4 region, I'm going to have the slope on the function is negative 1, so I'm going to have a y value, a down value, negative 1. Right here I'm at about negative 2, so moved. Then over here I'm at negative 4. I accidentally put another dot right there, and that's a huge whatever. And then I'm at negative 8. There's an asymptote on that one, so there's going to be an asymptote on the derivative as well. Actually, this continues to get steeper and steeper, negative 8, negative 8, then negative 16, so on and so forth. So it's actually kind of interesting. The derivative looks very similar, at least over here, as the original function, with the exception that here we're approaching 0 as we're going towards negative infinity. Up here we're approaching 2 as we approach negative infinity. I wonder if the same is going to be true over here on the other side of the asymptote. Well, let's cross over the tracks. Negative 6, nope, that's kind of right here. In fact, as we get closer to that asymptote here, it's going to get steeper and steeper. It would be like negative 8, negative 20, negative 100. So actually, it kind of comes up from negative infinity. Then we're at negative 2. Then we're at negative 1. And this actually starts to flatten out. It starts to approach 0. So I wouldn't expect you to totally know that, but after this example, you should. We would get something that would kind of look like that. And that's what we'll see later on, is that rational functions, things that look like this, their derivative is also a rational function. It's also a rational function. Though things get kind of whatever. All right? I'd like for us to I'd like to take some requests looking at the rest of these. I think well, you can't see any of those because flipping through the rest of that, number 7 kind of looks like the one that we just did. Number 8 kind of looks cubic. So what's that graph going to look like on number 8? Yeah, it's going to be a quadratic. Now, I wonder if it's going to be opening up or opening down. That's for you to find out. You are not going to have to do the rest of this paper assignment because you're going to have the thing that's online, which you can practice. But if you want, but the paper assignment might be helpful for you to do, and then because the ones online are just going to be the same type of graphs, maybe shifted up, shifted down, like slightly different, shape. What about number 9? Doesn't it look kind of weird? Let's do number 9, shall we? So if you haven't already, go ahead and put your local linear approximations. Kind of flattens out here, but then it kind of does that thing. One of the things that I like to do when I'm throwing numbers up here is I like to say, is there any place where the slope of the tangent line is 0? All right? And looking at this, it looks like we've got a 0 horizontal line right there, and we've got another horizontal line right there. Because normally, sometimes, in between there's going to be some trends. For instance, I'll just very quickly, looking to the right here, call it out to me, class, positive or negative? Negative. So let's call it -1. What about right here? Positive or negative? Also negative. I'll put -1 here. What types of numbers am I looking at in between, positive or negative? Positive. Where's it the steepest? Yeah, right there in the middle. It gets kind of flat over here, gets kind of flat over here. So I might throw a number like 3, and then 2, 1, 2, 1, something kind of like that. Now, are those exact? Absolutely not. This Mr. Goddard just sort of eyeballing it, throwing some relative numbers so that down here we can get a rough approximation on the shape of the derivative function. We will discover the formula to actually create this actual derivative graph, but not yet. So the zeros, I'm going to plot those first. So that's a 0 up on up or down. This is the derivative, so f prime. Mitzi, that's what we learned, that when we graph all those tangent lines down here, we call it f prime of x, and that little tick mark means prime. Calculus is you learn all sorts of notations. That sounds like mutations. We've got a 0 over here. A little bit to the right of the 0, we're at a -1. A little bit to the left of the 0 over here, we're at a y value of -1. And then, so I'm going to start over here. So moving to the right here. So I've got a y value of 1, a y value of 2, a y value of 3, a y value of 2, a y value of 1. So I happen to know it kind of looks something kind of like that, kind of bell curve-ish. So what? Yeah, your homework, like these are not multiple choice. These I actually wanted you to sketch. But I think when you do it online, it's going to give you like 4 different graphs.
For the first one, you put something like the quadratic, that's quadratic, the t. Do we also have to do something like that, like figure out what type of graph it is?
Are you talking about the first homework?
No. This one, the first problem.
All these problems are exactly the same.
So we have to put f prime.
You will choose the graph of f prime, which matches, which is showing the derivative of the original function. Yep. Okay. I think y'all can handle it. Oh, hey, look, it kind of looks like that one right there on number 11. I should just scroll down. Okay. This is the nice thing. Now, I will say this, in case y'all ever are absent or anything like that. online, I have posted these PDFs. I've done it because the virtual students do not, they said they didn't need a physical copy. But I've posted all of these online, okay, these little handouts that I give you. And after the actual questions, then the answers are there. Okay? Like you can see that. Would y'all like to see where these are posted? Yes, please, Mr. Goddard. Well, all right then, I will. I'll show you. So on the Google Classroom, you just go to Classwork and Handouts and Practice Problems. Oh, I guess that was kind of easy. And you click right there. And it's going to take you to a folder. And, oh, there it is right there. 3-1, 3-2. Oh, how about that, huh? And if you scroll down far enough, it's going to show you all those answers. Okay, so that's also another tool. If we don't get to all of the practice problems, I'm going to make sure that in class we're going to go through enough of them. But there you go. Plus, also, I know Mitzi. This is it. I know none of the rest of you all are ever late or anything, but lectures are all right there. And if you, I was doing some experimenting with this. It depends on your internet connection. And if you're willing to be patient for a minute or two, all right? But I do record these in 1080p, okay? So when you watch those videos, if you just wait for a second and click on the settings, you can increase the resolution. And there's a big difference between 360 and 1080. So anyway, hope you all are enjoying it. Not doing 4K just quite yet. If I get some more subscribers, find me on Patreon. We'll be able to get that 4K broadcast soon. Thanks for watching.